In this video, we will be looking at linear systems and how to determine the number of solutions or points of intersection. First, we're going to look at a graphing approach. So I have two sets of linear systems here, and we're going to state the point of intersection of each one. In the first system, the first equation, y equals negative 2 over 3x plus 5, it's already in y equals mx plus b. So I'm going to plot the y-intercept of 5, and then my slope is negative 2 over 3. So I'm going to go down 2, right 3, plot the point. Down 2, right 3, plot the point. And I'm going to continue, and I'm going to do it in the opposite direction from the y-intercept as well. So instead of down, I'm going to go up. Instead of right, I'm going to go left. And there we are. Here's my first line, and I'm just going to label it as number 1. Now let's look at the second line. The second line is in standard form, so I do have to rearrange it into y equals mx plus b form. So I'm going to start off by bringing the 2x and the negative 15 over to the other side, so that we have 3y equals negative 2x positive 15. And now I'll divide both sides by 3. And we end up with y equals negative 2 over 3x plus 5. If we look at the equation, it's the exact same. So the line that we already graphed is equation 1 and equation 2. So if it's the exact same lines, one on top of the other, that means there are an infinite number of points of intersection. All right, let's see another scenario. Y equals 2x minus 3. For equation number 1, our y-intercept is negative 3, and our slope is 2, or 2 over 1. So I'm going to go up 2, right 1. And I'm going to do that over and over again to the right. And then on the left side, I'm going to go down 2, left 1 to continue that same pattern. And there's equation 1. Equation 2, I am going to have to rearrange. So I'm going to bring the 4x over, and it will become negative 4x. The 12 isn't changing because it's not moving sides. And now I'll divide everything by negative 2, and we end up with y equals positive 2x minus 6. So the same slope, but a different y-intercept. So I'll start at negative 6 on the y-axis, and I'll do the same up to right 1. And in the past, we have established if we have two lines with the same slope, then they are parallel. And if they are parallel, there's no way for them to intersect. Therefore, in this scenario, there are no points of intersection. So our two scenarios here are, you have two lines that when arranged in y equals mx plus b, they're the exact same, which means we have an infinite number of solutions. Or when they're rearranged, they have the same slope but a different y-intercept, which means they're parallel, but because they're starting at a different point, they're not the same line, which means there's no point of intersection. And of course, the past few days, we've also looked at many linear systems that have one point of intersection. Now let's try an algebraic approach, because we're not always going to have that graph where we can rearrange our equations into y equals mx plus b to graph and visualize it. So in the first linear system, everything is set up really nicely in that the x's, the y's, the constants, the equal signs, the zeros, it's all lined up nicely. So I'm choosing to do elimination here. And if I'm doing elimination, I'm going to choose to eliminate my x's. That's my choice here. So I'm going to multiply the second line by 3 so that we can get 6x. So my first line, I'm just going to copy paste it. And my second line times 3. So 6x plus 9y minus 45 equals 0. Now, because I'm choosing to eliminate the x's, addition will accomplish that because the signs are opposites. Now, when I do that addition, everything ends up canceling out. Negative 6 plus 6, 0. Negative 9 plus 9, 0. 45 minus 45, 0. So we end up with this true statement of 0 equals 0. Now, if I were to actually graph these lines, and you can tell right here, if I had just multiplied by negative 3 instead of positive 3, these equations would be the exact same. And if the equations are the exact same, the y equals mx plus b will be the exact same, meaning we have the same line. And if we have the same line, that means it's an infinite number of solutions, like the scenario above that we had graphed. So when you get this true statement, the x's, the y's cancel out, but you have a true statement that 0 equals 0 or 5 equals 5, that means you have an infinite number of solutions. If the x's or y's didn't cancel out, then of course we would solve for an actual value and there would be a point of intersection. But the connection to see here is I could have multiplied the second line by negative 3 and I would have gotten the exact same values from that top line. Let's try the next one. The next one is set up nicely for substitution. I have an isolated variable, y equals 2x minus 3. So I'm going to take this and replace the y in the second equation with it. And let's see what happens. I'm going to distribute that negative 2 in so that I have 4x minus 4x plus 6 equals 12. Well, 4x minus 4x is 0, so that's gone. And then I end up with the statement that 6 equals 12. Or if I had brought this 6 over, I would have 0 equals 12 minus 6, which is 6. Either way, these are false statements. And when we have this false statement, unlike the previous scenario, it means we have 0 solutions. There's no solution here because the x's canceled out. There's nothing for me to solve for. And then the fact that the statement is false, it means no solution. Now, another piece of evidence here. Maybe you don't believe me. Let's take this second equation and rearrange it in y equals mx plus b. So I'm going to bring the 4x over, and now I'll divide everything by negative 2. And when I do, I get y equals 2x minus 6. And if we compare, both lines have the same slope of 2, but the y-intercepts are different, meaning they are parallel but distinct lines that will never ever touch. So here we are. Algebraically, if you see this, a true statement where the variables have disappeared, infinite number of solutions. If the variables disappear but you have a false statement, there's no solution. So let's summarize this. So let's summarize. There are two options here. Option 1 is convert both of your equations into y equals mx plus b, or maybe they're both in y equals mx plus b. And in that case, we can compare the slopes and the y-intercept. If our system has one solution, it might look something like this, with one point of intersection. You will know there's only one solution when you have different slopes. The slopes are different, the lines have to intersect. If you have 0 solutions, you have lines that are parallel and distinct. So they will never touch. If they're parallel, they have the same slopes. But if they're parallel and distinct, they have a different y-intercept. And finally, infinite, you have the exact same line. It's one on top of the other. Which means we're going to have the same slope and y-intercept. Now, if you were doing the algebraic approach, you'll have one solution if you actually get a value for x and y. You get x equals a number, y equals a number. You'll have 0 solutions if you have a false statement. So your variables disappear, but you get something like a number equals 0 and not 0. So like 5 equals 0 or whatever it might be. Whereas it's an infinite number of solutions if you have a true statement. So like 0 equals 0, that is true. Another thing we can look at is if the forms are in standard form, we can compare the coefficients and see, can I multiply one line by a number to get the second? If you do, you have an infinite number of solutions. If you can just multiply by a number to get the same x and y coefficients, that means they're parallel but distinct. And we'll see that in a few examples. So in this first example, they're both in y equals mx plus b form, and I notice same slope but different y-intercept. So that means they're in the same direction, they're parallel, but they're distinct because they're starting at different points, which means we have 0 solutions. For the next one of my equations is in y equals mx plus b, the other isn't. So I'm just going to convert this second one into y equals mx plus b. And then divide out the -2, and I get y equals 3x minus 5. They're the exact same. There we are. Now that was one approach, but I could have also done substitution. I could have tried solving this and just subbed it in. So 6x minus 2 times 3x minus 5 equals 10. And I would have 6x minus 6x plus 10 equals 10. 6x minus 6x is 0. I get 10 equals 10. That's a true statement, so an infinite number of solutions. So 2 different ways you can deal with that one. Next, 3x minus y equals 5, 2x plus 3y equals 6. Okay, let's see. Let's pretend I were to solve this. I'm going to multiply this by 3. And I would get 9x minus 3y equals 15. 2x plus 3y equals 6. I can see they're not the same, so I think I will be able to actually solve. When I solve here, the y's cancel out, and we have 11x equals 21. So this is going to have one point of intersection. I'm not going to continue the solving here, but the fact that I'm actually going to get a value for x means there is one solution. Now, just this step here could have also told me, when I multiplied by 3, these portions did not match, which means there's no way for x and y to cancel out. So there has to be a solution. In the next one, if I multiply this first line by -3, it will give me -9x, -12y equals -36. They are the exact same. Copy paste. I was able to multiply one line by a number and I get the second one. And because they're the same, infinite number of solutions. Okay. For the next one, I see y equals mx plus b for one equation. So I don't feel like doing substitution. I'm just going to rearrange the second one into y equals mx plus b. That's my personal preference. You could have done a substitution here. That's no problem at all. Now I am going to make sure to reduce my fractions. So 10 over 15 is 2 over 3. And now -15 divided by 15 is -1. And when I compare, same slope, different y-intercept. So our lines are parallel and distinct, meaning 0 solutions. For the next one, okay, I'm going to see. I'm going to multiply by 2. And that gives me 6x minus 10y, so the beginning parts are matching, minus 4 equals 0. So if I were to actually try to eliminate here, and I did subtraction, the x's cancel out, the y's cancel out, and then I'm left with 10 equals 0. False statement. That tells me there are 0 solutions. But even if I didn't do the actual elimination part, once I multiply the first line by 2 and I get this, the fact that these match tells me it's parallel, and the fact that these are not the same tells me it's parallel and distinct instead of parallel in the exact same line. Next one. Well, these look ready to go for elimination, but I noticed the x's are the same, but the y's aren't. So if I were to eliminate with subtraction, let's say, the x's are gone, but I would have 2y equals 0. There is a point of intersection here because I'm actually going to get y equals 0. I can sub that in and then solve for x. And our final one, because one of my equations is in y equals mx plus b, I'm going to isolate for y in the second equation as well. But of course, I can do substitution here if I prefer and compare the algebraic answer I get. But I get y equals 5x minus 9, exact same line, meaning infinite number of solutions. And that's it. So when we have y equals mx plus b, it's very easy to tell by looking at the slope, seeing if they're parallel or the same slope or not. You want to see, is it the same line for infinite, parallel and distinct for 0, or different slopes, so there will be a point of intersection. Algebraically, we're looking to see if we actually are able to solve for x or y, or if x and y cancels out and we're left with a true statement for an infinite number of solutions or a false statement for 0 solutions.